Okay, so good morning, everyone. My name is Samuel Pellissier. Today I'm going to present to you our work on device identification in LoRaWAN through message linkage. It was done with Mathieu Kunge, Vincent Roca, and Didier Donzé in France. So quick words of introduction. It shouldn't come as a shock for people in this room, but IoT devices are used everywhere today. There are more than 10 billion of them worldwide, and 225 million of them are LoRaWAN devices. When we think of IoT, we may think of smart homes with ways to automate lighting or manage the watering or electric systems. But the applications are much broader than this. We can indeed monitor the health of people. We can track cargoes around the world or crops in the field. And we can also manage electricity or water. And with great connectivity comes great responsibility. So we still more than ever have to protect the privacy of users. Even though IoT devices can be using wires, today's talk is focusing on identifiers in wireless network protocols, and more specifically in LoRaWAN. And in this case, there are ways to track the user's position. It has already been done with Bluetooth or Wi-Fi, for example, to track the user in shopping malls. As said in the previous talk, we can also use the radio signal features to fingerprint devices. And finally, we could infer activity through metadata. For example, if a garage door is connected, the existence of only one message is enough to know that the owner of the house is leaving or coming back home. More specifically, in LoRaWAN, we can use the identifiers to gather more information about the device and its application. And we can then map it to an already known identity, activity or location. For example, if we know that one specific company is deploying some kind of end device somewhere, we can take the traffic of this end device and link it back to the actual identity of the company. This is a sort of passive collection. It's quite cheap for an attacker because gateways cost around $100 to $300, and it's quite easy based on the nature of the protocol. Because LoRaWAN is part of a bigger family, which is the LPWAN for Low Power Wide Area Network. There are lots of protocols in this family. You may have heard of Sigfox, NB-IoT, Dash7, and LoRaWAN. They are long range, so a few kilometers. They have a low bit rate and a low energy consumption. And finally, they are mostly low cost. So the end devices are put somewhere in the wild, forgotten there for a few years on battery. This is a typical architecture of a LoRaWAN network. On the left, you can see the end devices. They are connected through a radio link to gateways, which then translate this radio signal into a classic IP TCP packet. And it goes all the way through various servers. And then the servers can treat the data and answer back to the sensors. For today's talk, there are two relevant identifiers. The first one being the DevUI, which is unique for the lifetime of the end device and set by the manufacturer. And you can view it as a kind of MAC address. And the second one is a dev address, which is randomly generated for each session. So each time the end device joins the network, there is a new pseudonym generated for it. Below is the global way, the most used way to join a network. There are different types of servers here, but only the joint server is relevant for today. So first of all, the end device sends a join request containing clear text, the DevUI. This goes all the way through the joint server that identify the end device. And if the identification is correct, the joint server answers back with the join accept containing the encrypted version of the dev address. So then the end device decrypts the dev address and can use it in the upcoming communication. So in every single following message containing data, which is called uplink, there is a clear text version of the dev address. So from an outsider perspective, an attacker that listens the radio link in between the end device and the gateway, there is theoretically no way to link back the join request with the following uplink, and thus the DevUI in click text here with the following click text of the dev address here. And what we are trying to do is basically this. To do so, we have a quite simple threat model. The end device is left unmodified and the payload stays encrypted. So we only deal with the radio and the clear text that goes over it. And the attacker is passive, which means they do not inject or alter any message. They can only eavesdrop the physical link in between the device and the gateway, and they can control several gateways. And as a side note, the fact that the LoRaWAN is long range only increases the attack surface. It doesn't really change the fault model itself. So how can we do this? We have to consider that we have a data set of messages. In our experiments, we use a data set with the ground truth, so we already know the links. And in this data set, there are two types of messages. One type is the join request, and the other are the uplinks. So we pick one join request, and we want to find the following uplink that corresponds to the same end device. To do so, we can use some data from the header of the messages. For example, there is something called the frame counter, which is increased every time one end device sends a message. So it starts at 0 and then goes up. So we take one join request, get the following uplinks, and try to find one uplink that has a frame counter equals to 0. So this means the join request and the uplink have a high chance of coming from the same end device. Another way to look at it is to check the timing in between messages, because one end device do not have any incentive to wait after receiving the join accept. So the join request and the following uplinks are quite close time-wise. We can also look at the radio signal features, because we consider that each end device has a kind of radio profile. So two messages coming from the same end device should have the same radio profile, so the same radio features. For example, in this illustration, the end device 1 is farther away from the gateway than the end device 2. So there should be a difference in RSSI between those two end devices. So we once again take the list of messages, we pick one join request and try to look for more or less similar radio profile in the following uplinks. And we can then link back the two messages. This is the whole list of features. I won't go into the details here. There are 4 categories, one being the radio, another one being the actual modulation of the signal, the LoRa signal. Another one is the information contained in the headers of the LoRaWAN. And finally, we have some application specifics about the timings. All these features are then used to train a classification model. This is a classic binary classification problem. We use various classifiers on the right here. The goal is not really to compare them, but rather to find one for which the attack is working. And that's the case. On the left here, we have the various classifier and the true positive rate as well as the false positive rate. And we can see that multiple ones provides interesting results. The true positive rate is quite high, and the false positive rate is really low, which means we have a high confidence on the result that we find, on the links that we find. During this process, we have found that the frame counter plays a great role in determining which link is or is not correct. So we try to remove it, and this is also the result on the right here. We can see that the true positive rate drops quite a bit for all the classifiers, and the false positive rate remains the same. This means that the frame counter could be used as a control measure. To do so, we can encrypt it or try to start at the random offset. So instead of starting at 0 for for the first uplink message, we could start at a random value determined during the joining phase. As a side note, this is not backward compatible for the current standard. We could also try to introduce some randomness inside, for example, the radio features, but changing the radio signal power may make us lose some messages. We could add some random delay in between the join accept and the following uplink, or pad the payload, or maybe use multiple first uplink messages, and some of them would be decoys. But all these solutions introduce a lack of performance in the protocol. And finally, as we are dealing with identifiers, we could try to obfuscate them. And one way to do it is to use reservable addresses, such as in Bluetooth Low Energy, or maybe to use a shared address for multiple end devices, and then server side use the network session key for identification. And once again, this is not backward compatible. As a conclusion, we have shown that we can reliably re-identify devices using various features. The frame counter is greatly responsible for the attack's performance. And finally, the countermeasures that we are proposing often require to change the LoRaWAN specification as well as reducing the performances. Thank you, everyone. If you have any question, I'll be glad to take them.
Thanks a lot for that short presentation and with very dense information, I have to say. Yeah. Do we have any questions right now? So one thing that stuck to me immediately when you mentioned it's not compatible with the, your mitigations are not immediately compatible with the specification. I have to admit I'm not overly familiar with LoRaWAN. So those changes that you propose to the spec, could they be introduced incrementally? Could that be done on top of existing networks where you can protect singular devices that use your adapted specification while still remaining compatible with the rest of the network? Or would you really need a changeover date to switch from one spec to the next spec to do that?
No. It actually depends on which thing we want to implement. For example, if we take the frame counter one, we could use the random offset directly. So instead of starting at 0 for the first uplink, we start at, I don't know, 100 or random value, right? So this is already supported by existing networks. We could use this directly today, but other things may require to change and may break the compatibility with previous version.
Okay, so the other changes would really require changes to the gateways, not just to single devices. Yeah. And those changes to the gateways would then potentially break communication with non-modified devices.
Yeah, is that right? More than the gateways, it would be the various servers that you're using.
Server side.
So,
okay. Yeah. Would that work with? Does LoRaWAN have a version identifier in some of those protocol fields? Could you do? Yeah. Could you run two protocol versions in the same network?
Version and then redirect the message.
So servers could have a fallback to older clients.
And I think in some implementation that's already the case between the 1.0 version and 1.1.
Right. Okay, so most of your do I get this correctly? That most of your changes could be added to existing networks without breaking non-modified devices.
Yeah, but I mean, it still needs to be a new version of the standard.
Got it.
Yeah.
Are you in contact with the standardization committees?
Not at the moment. But
okay.
We'd like to.
Is that a plan to maybe get a new version in there?
We are still working on other problems with our spoilers, but that will be a good thing to actually work on the standard.
Excellent. Do we have any other questions at the moment? Again, if you have any later questions, please just reach out to the authors through email or any other channels. Then thank you very much again.